estimate should be degree of belongingness, not just a plain label, right?
Yes.
In that case, I want to start with this example. Let's say we have one independent variable, number of hours studied, and the dependent variable is binary, pass or fail. So the students who studied around 10 hours, they're passing. And students who didn't study at all, 0 to 2 hours, they are failing. But many data points live in between, right? So drawing a line, stupid line like perceptrons around here or wherever will not explain the phenomena. For that, this kind of curve called sigmoid, because it looks like S line, it can solve our problem or this family of lines. So on y-axis, we map, for example, for 2 hours, we map the corresponding point for on y-axis. The probability to pass for studying 2 hours is about 0.18. And conversely, the probability to fail will be 1 minus 0.18. For this whole continuum, we can get the probability if we do it in this way. Interestingly, very interestingly, we don't need to move far away from the line equation. Same W transpose X, the line equation, if we put it in this equation, sigmoid form, it's 1 over 1 plus e raised to power minus W transpose X is this line, the sigmoidal line. In logistic regression, we call it the link function because it links linear line to the classifier, to the other domain where we have probabilistic interpretation of the classification result. We kind of transport from one domain to the other domain, the logistic, right? We transport result from one domain to the other domain. That's why logistic regression. Another solution for binary classification, and interesting thing that we can do with logistic regression is that the idea applies not only to real, but as well as nominal variables. I will give a short example that you can also have a look later for the nominal variables. If we have this link function, here W transpose X is written in simpler line form, mx plus b, m is slope, b is intercept. We want to start with nominal variables. For nominal variables, the probability for an event of interest is number of data points for that event divided by total number of data points, right? For example, in this example data set, we have two variables, male, female, and the students in the honors program or non-honors program. This is the dependent variable. So if we look at the total, there are total 150 non-honors student, 49 honors student, total 200. So the probability for a randomly picked student to be in the honors class will be 49 by 200. All right, we keep this number, about 0.24, whatever, and then we try to reach to this number through logistic regression. N over N, about 0.24, 49 by 200. Now, if you remember, the definition of odds is P over 1 minus P. Probability of being in honors class divided by probability of not being in honors class. That particular odds, this number, P over 1 minus P, is actually e raised to power W transpose X. And we can get probability from odds by, this is the probability, this is the odds divided by 1 plus odds give us the probability. And if we expand it or solve it a little bit more, we get 1 over 1 plus e raised to power minus W transpose X. So 1 over 1 plus e raised to power minus W transpose X is actually giving us the probability for being in class A or B. So what is W transpose X? Mx plus B is actually log of the odds. Log of e raised to power mx plus b, when we take log, we get mx plus b, right? So log of p over 1 minus p for the nominal variable should give us the mx plus b. How? We can look at this particular example that we try to solve. If we want to create a logistic regression model without using any variable, then the intercept, we have no information about independent variables, just the dependent variable, and we want to find out the model parameters, W. since we don't have any independent variable, there will be only W for ones vector and the intercept representing intercept, and that is minus 1.125. If we put minus 1.125 in the equation that we just looked at, we get 0.245, which is the probability. Could you connect? So overall probability of being in honors class, we can calculate with pen and paper, 49 by 200, but logistic regression way, we will get the same number. That's what my point here is. Log P of P over 1 minus P. If we put 0.245 divided by 1 minus 0.245, it's going to be the same thing that we got with logistic regression. But if you do simple regression with no independent variable but vector of ones, we will get 0.245 as the estimate for W, and 0.245 is mx plus b. So mx plus b divided by 1 minus, we get the intercept, which is log of odds. So both regression and logistic regression are connected through this equation as long as we are dealing with nominal variables. Now, let's look at the case of real numbers and the problem of estimating W's in regression. If you remember, we did it maximum likelihood way. So let's do the same here. Linear decision boundary. So minus W transpose X or W transpose X, they are same as long as they are equal to 0. So the probabilistic solution, we set up the ground by having labels 0 or 1 values. And then for class 1, we will represent probabilistically. Given X, what is the probability for Y to be 1? Will be, this is sigmoid functions representation. You can use any other if you like, but it is same thing, 1 over 1 plus e raised to power minus W transpose X. When we input the W transpose X here, if you remember, for the perceptron case, we looked at W transpose X when it is 0, that is the class boundary. If we have 0 here, then the result for the sigmoidal equation will be 0.5. So greater than 0.5, we have one class, less than 0.5, we have the other class. Because we just looked at the inner workings of 1 over 1 plus e raised to power minus W transpose X. It gives us the probability, right? This thing, for perceptron, being equal to 0 was the class boundary, giving us the class boundary. Same class boundary when we put in the sigmoid equation will give us result greater than or less than 0.5, and we can then decide not only the class but the degree of belonging as well. On the boundary line, both the probabilities will be same. So being in class 1, in class 2 will be equal. 0.5 divided by 0.5, we have 1. And if we replace the probability with the corresponding equations, so 1 minus 1 over e raised to power minus transpose W transpose X is probability for class 0. We keep it here, and for the positive class, we keep it here. When we solve, we get 1. Why? Because e raised to power minus W transpose X, when W transpose X is 0, when we exponentiate something to 0, exponentiate to 0, power 0, we get 1, right? So things are perfectly connected now. For perceptron, we lived with only the plain class labels, but using this equation, we can not only give the class label, but as well as the degree of belongingness. We also have some flexibility of changing the threshold for class imbalance problems. I will continue from this point on for the same course of discussion, but class imbalance problem and the decision threshold is an important caveat here that we need to discuss from application point of view. So please remind me when we finish to touch upon that point, because for perceptron, it's a dumb number. Whenever it's 0, we are in class A or B, less than 0, greater than 0. But this particular thing, since it becomes a probability, now we can decide, depending on the problem, the threshold, is it 0.4, 0.3, 0.6? We can change it and get better results. But for now, keeping it 0.5, the design matrix and the dependent variable being discrete, having allowed to take values between 0 and 1, this is the thing that we have. How do we estimate W's now? For logistic regression, probabilistically, then we can have the same. First, try to reach to the likelihood function. It's a binary problem, so we use Bernoulli distribution and the sigmoid function raised to power y multiplied by 1 minus sigmoid function raised to power 1 minus y. We know this from the previous sections when we sessions when we open Bernoulli equation. So this is going to be very useful for one example. For all observations, we assume that every example is independently and identically sampled, so we can easily multiply all the probabilities to get the probability of y given x in W for the whole data set. Taking log of both sides, it becomes log likelihood. So the yi becomes, when we take log, yi exponent becomes a multiplier. This multiplication becomes a summation. This multiplication becomes a summation, and this exponent becomes a multiplier. So the best W's will give us the best likelihood. If that is the case, maximum likelihood way, we need to now look at our problem. It's not as simple as we did for regression. Here we have another thing in the mix. We are not working with W transpose X only. We are working with sigmoid function. So we cannot take derivative plainly of W transpose X as we did before. We need to take first derivative of W transpose X with respect to W, and then of sigmoid. So chain rule will be applied. So in 2 steps. So for derivative of W transpose X, we know that it is X. With respect to W, only X is the constant now, W goes. For the second term, sigmoid functions derivative with respect to W transpose X, we need to do it in a way that when we open this sigmoid function, 1 over 1 plus e raised to power minus W transpose X, it's inverse of 1 plus e raised to power minus W transpose X, right? And when we take the derivative, that minus 1 comes here, and here we add 1, so it becomes minus 2. Only this term is dependent on, so we take the derivative of this term, e raised to power minus W transpose X, again multiplied by this 1, minus 1. So the solution, further solution for these spread out terms will look like this. Further cutting it down, we come to this point, 1 minus sigmoid multiplied by sigmoid. First term, xi, second term, 1 minus sigmoid multiplied by sigmoid, third term. For the third one, now we are going to replace these with their partial derivatives. So yi here, log sigmoid's derivative 1 over sigmoid, and then from the chain rule, we get to put these 2 terms here. Similarly, log of 1 minus sigmoid becomes this term. And since dx of that will give us minus 1, we put minus 1 here. And then from the chain rule, the other 2 terms. Other 2 terms we replace with their solutions that we arrived at in the previous slide. So for this one, we have xi. For this one, we have 1 minus sigmoid multiplied by the sigmoid function. Same here. Solving further will give us the differentiated log likelihood of the logistic regression as y minus sigmoid of W transpose X. But the problem here is that this thing is not a solution. It depends on W transpose X, right? So we are stuck. No solution here. So after differentiating, we are again depending on something that we are trying to find. And how to maximize that, so it's no-go. But still, this may be useful somewhere. So let's keep tabs on that. So the maximum likelihood function, we know it's the summation of these 2 terms. We agree that y multiplied by log of sigmoid and plus 1 minus y multiplied by log of 1 minus sigmoid. If we want to take the derivative, we get this. If we equate it to 0, the maximal point v will be on this solution of this. Let's use it somewhere, but this is not going to solve our problem of estimating W's. What's the other way if we cannot do things analytically? We do it
iteratively.
Right. So we go to gradient descent now. Gradient descent will have like 1 step at a time, either stochastic way or batch way, both same approach that we did with regression. And but the likelihood function is this one now. So very much similar to the perceptron. We initialize randomly, or you initialize with 0, 0, 0s. 0, 0, 0s can come randomly as well, right? So it doesn't matter actually. We assume that the weights are somehow we have those initialized with some sensible numbers. And if it never converges, we can always start with different. But what we do next is calc and classify. We calculate the degree of belongingness by putting W transpose X into the sigmoid function. It gives us what? The probability. The probability greater than 0.5, we classify as 0. Otherwise, greater than 5, classify the example as 1, otherwise 0. And the only difference is here, right? If you remember, this is the equation that this is the term that we received after differentiating the log likelihood function, right? Y minus sigma of W transpose X. Well, this is very much similar to perceptron, but we are looking at a summation. So Y actual value minus the estimate summed over all multiplied by X. If there is a mistake, only if there is a mistake, we are going to calculate the amount of mistake not as 0 or 1, but it will be between 0 and 1. 0 means no update. Between 0, greater than 0 and less than 1, the mistake, because sigma will return some number between 0 and 1. So that is kind of soft update, right? Not like perceptron, so update size 1 multiplied by xi. No, it's between 0 and 1, some number multiplied by xi. And then that's all there is. This is the update rule. And if we want to represent this in matrix form, we can say the x will come here, x transpose, and this minus will go in and make this term positive. So y hat comes out of the sigmoid, y hat comes first, yi, actual ground truth y's, will go after minus y, and x transpose y hat minus y. When you implement in the batch gradient descent for logistic regression, you will be doing this. X transpose y hat minus y multiplied by eta, an arbitrary number, will give us the new W. And if you want to have some sensible weights, you can penalize the same way we did in regression. If you remember, in ridge regression, we added this term, right? So lambdas divided by 2 and the magnitude of W. Oh my God. So since from the start, we are looking at W transpose X, and we connected it with the same regression solution we could solve classification problem with. If it is binary, even multi-class, we can use it for multi-class as well. Perceptron gives us 0, 1 only, but logistic regression is again based on the same W transpose X, but in probabilistic domain. So we put it in logistic function, 1 over 1 plus e raised to power minus W transpose X, this guy. And same regression is doing classification probabilistically for us now. The other way is, I mean, for the large data sets, this can give us some trouble, gradient descent. And anyways, the other option is Newton-Raphson's way. This method is the actually implemented method in MATLAB or Python or Spark, guys who, when you need to have some performance optimizations and work on large data sets. So IRLS is the solution most commonly implemented in libraries. It not only needs first derivative of the likelihood function that we have, it also calculates second derivative. So the general Newton-Raphson's proposal is that the new value of the weight will be as much as the ratio of first and second derivative subtracted from the previous value. And this is the abstract idea, how we apply it in iterative reweighted least squares, and why we call it reweighted least squares, because previous solution we looked at is iterative, right? So reweighted least squares, why? We'll find the explanation shortly. This particular matrix is what we are going to do extra than gradient descent. The same design matrix for the columns are the features, rows, and we calculate second derivative. So for the first variable, second derivative of its first derivative. On the diagonals, we have self second derivatives. On the other terms, we have with respect to the pairwise. So x1, derivative of x with respect to x1, and then x2, and so on, x1 and xn. In the second row, we will have with respect to x2 and then with respect to x1, and so on, and so on. So the whole matrix of second derivatives, pairwise, corresponding to the design matrix, is called Hessian matrix, represented by H. Very common notation that you will see in textbooks. H is giving us the second derivatives. If we could calculate that, we replace things here. So first derivative, we know the negative log likelihood function. We just calculated for the gradient descent solution. And the second one is h, so we bring it for the numerator up and it becomes h inverse. And for the derivative of negative log likelihood, if you remember x transpose, y hat minus y, right? Here, this guy. We reached this guy when we derived the first, when we differentiated log likelihood, right, from here. We couldn't find it useful at that time because it depends on w transpose x, which we are trying to solve for w, and the solution that we thought will lead us to w is again depending on w, right? So we left it there, but it was not that useless. We used it here in the gradient descent, and then in the Newton-Raphson's method here, we are using it by replacing the values for first and second derivative, and x transpose y hat minus y is for negative log likelihood's first derivative, and for h inverse we can do this. We expand this with the corresponding inner terms, and when we take the partial derivative with respect to w for this guy, it will lead us to putting x inside with both the terms. With respect to w, only this term depends on w. This is constant, so it disappears. We remain with sigmoid of w transpose x multiplied by x. So yeah, we reached here, and h will be the sigmoid of our w transpose x, 1 minus sigmoid of this multiplied by xi into x transpose. And this particular guy we can represent in terms of matrix like this: x transpose for this blue term, r is the weight that we are referring to in the name, iterative least, reweighted least squares. So these are the weights. It's a diagonal matrix that is giving us the weight with respect to given input, how much weight for the update that we want to change, how much. For every input, when we make a mistake, we reweight the updates as much as this multiplication. We represent it with r multiplied by x. So x transpose rx, if we replace here like this, inverse, and this much is okay to update with IRLS, but we take it a little further, and if we expand this, we get this particular equation that is should be very much familiar. If you remember, x transpose x inverse. So here we have R, which is a diagonal matrix. So it doesn't matter. Output is x transpose x because these have only diagonal terms. Others are zero. The weight matrix. So x transpose x inverse, x transpose in y. So R x w j will give us y. If you remember, we called this equation the normal equation, right? We used it for solving the regression problem. So IRLS is bringing us to the same solution, right? That is interesting. So we don't need to go this far when we implement IRLS. This much is okay. So new weight will be changed as much as inverse of the Hessian matrix multiplied by the derivative of negative log likelihood, which is x transpose y hat minus y. But going one step further is for us to realize that even logistic regression solution from the starting point was very much depending on w transpose x, and when we reached to the conclusion, it became the normal equation that we used for regression. So essentially, we are doing the same thing for regression and logistic regression. One is the error is measured in terms of squares. Here we are measuring the errors in terms of 0-1 summation y hat minus y, but otherwise all things are connected and same. So in summary, we have learned today Perceptron for binary classification, an interesting interpretation of geometry and application, and then we looked at the limitations of Perceptron and how can we overcome, or we found a better solution in terms of logistic regression, which gave us the probability of belongingness in addition to the label of the class. We tried to solve it through maximum likelihood, which didn't work out because the differential of The likelihood function depends on W itself. But we could do it through gradient descent and iterative reweighted least squares way. And hopefully we will know from now on what's going on behind the scenes when we run a line of code and get the parameters. So here, logistic regression not only gives us the probability, but the individual weights have a meaning. For example, intercept will represent the odds ratio, right? So we learned that logistic regression is in reality ordinary regression, but we are using a link function or logit as a response variable. So W transpose X is put into the link function and we get probability, but that particular linear relationship between X and Y is transformed. And now what I want you to pay attention to, the next power of logistic regression. Let's say we concluded these two W's. So we have just one variable, gender, and gender is nominal variable. So the weight for gender is 0.59828, and for the 11111 feature, we have augmented feature, we have the weight minus 1.47, the intercept. In case of perceptron, this means nothing, it's just a boundary. But in case of logistic regression, minus 1.47 means something. It's the probability of male in the honors class, being in honors class. Or the log of odds for a randomly picked male being in honors class, the log of odds will be minus 1.4709. And for the W for independent variable also represents log of odds. So we can verify this with the data set. For female in honors class, if you want to calculate the log of odds, P over 1 minus P, the probability will be 32 divided by 109 and 77 divided by 109, P over 1 minus P. That number we should reach to through the logistic regression solution, and that number is 0.59 that we get here. So the probability of female in the honors class is this one. If female gender is male, in that case, this will be multiplied by 0, and the probability of a randomly picked male will be minus 1 point. The log of odds for a randomly picked male to be in the honors class is minus 1.47. So looking at the data, you can see fewer males are in the honors class, right? Fewer emails compared to female. And the intercept, which also represents the participation of males in the honors class, is minus. So these are not just numbers, they have a meaning and connection to the context and data. Especially in case of nominal data, you will be able to interpret your model in terms of probabilities and log of odds very effectively, which is not available in other